please.
Okay. Yeah, thanks for the nice introduction, and thanks for organizing this interesting conference. I'm very pleased to kind of be the final speaker. Let me try to get a pointer to make it simpler for everybody. So I guess you see my slides and you see my pointer. Okay, so I will tell you about the AC-Josephson effect and kind of how it relates to quantum property of light. So that's the title. So I will give a short introduction and then show you the setup for the Josephson parametric down conversion. I have to say, you know, I'm a theorist, so it will be theory, but there's actually an experiment which was doing exactly this. I will show you a bit the methods, and then I think the results which are most interesting at. So I give an introduction on parametric resonance, but I think on this audience, this is maybe useless, but I still want to do. So we have a damped harmonic oscillator. So omega naught is the oscillation frequency, gamma is the damping. And then we drive it periodically, but we don't drive it externally, but we drive the resonance frequency. So we change the frequency periodically. And the fact is you have to drive the frequency at best is to drive it at double the frequency of the harmonic oscillator. And what you then get is actually that you pump energy in this oscillator. And the best way to see is that you actually claim that you have a solution already, which oscillates at a natural frequency. And then you see what happens to the amplitude of the oscillation. And what you can derive very easily is that due to this pumping here, actually it's essentially like a force, but the force is then proportional to the amplitude which you already have, such the amplitude actually grows exponentially or decays exponentially, depending on whether you drive stronger or the damping is stronger. And this is this famous diagram where you actually see at which point you actually expect instabilities. So the lines here are the finite damping, and then the dashed lines are without any damping. Okay. So this is the idea. So if you start driving the system, then first nothing happens classically, and then you hit the critical point where you actually where the amplification counteracts exactly the damping, and then you start to get a final result, which is actually, I mean, in this model it goes to infinity, but then it's saturated to pump depletion or nonlinearities. So there's a natural implementation of this physics in Josephson circuits, and the relation is a bit not so obvious, so I want to explain it in detail. So it's a voltage biased Josephson junction, and then you have like then you have it coupled to a harmonic oscillator. Yeah, so a harmonic oscillator in electronics is like an LC circuit, and you have some damping, which is the R. So the R actually corresponds to damping rate, which we had before. The voltage is actually the frequency. So what is one of the most useful things in this setup is that you can actually tune the frequency in C2, the frequency of the drive, yeah, because via the AC-Josephson effect, you have the frequency of the drive. And the omega naught is the bare frequency of the harmonic oscillator. The driving strength is actually the Josephson coupling. And if you use a split Josephson junction, you even can also tune this driving strength in C2. So this is the setup for what is called the degenerate parametric amplifier. And in that case, it's the following. So you can think about this in this sense, the following way, that the voltage actually makes Cooper pairs having the energy 2 eV. And this 2 eV leads to the fact that it actually matches 2 photons. So you actually, by each Cooper pair punneling through the junction, you excite 2 photons in the resonator. But for the rest of the talk, I want to use a related but different setup, which is just the same thing, but having 2 resonators. And now you don't have the resonator at half the frequency of the drive, but you make it in such a way that the sum of the 2 resonance frequencies actually matches the voltage which gets applied, which is like the frequency of the drive. And the idea is then the following. So each time a Cooper pair tunnels across this Josephson junction, you have enough energy not to excite one of these resonators, but it only works if you excite both of them. Yeah? And what you see is that in this kind of way, you actually produce always 2 photons together, and those then leak out in a resistor, which in real applications is a transmission line. And you might expect that they get entangled because they're kind of created by this non-degenerate parametric process. So, and this was measured, or part of it was measured. So this is a measurement which was done in 2017. It's published in Physical Review Letters. What you can see is that, so they did exactly this setup. They changed the voltage. And what they actually see, they see emission of one of the modes or of the other of the modes. But then if they tune it correctly, they get one voltage where they see emission in both of the modes. And that's exactly this condition that this resonance condition that the sum of the frequencies of the resonator actually measures the Josephson energy. And then they did measurement. For example, they measured the second order coherence and also other measurement. And there was a bit of theory, but what we do here is we extended the theory to one parameter which was not treated in details before, which is actually the detuning, which I introduced in the following. And also we kind of get a more explicit theory at final temperature. Okay, so this is the setup which we do on a theoretical level. We kind of say we have the voltage by a Josephson junction. We model the two resonators via these idealized circuits. And then what we say, we couple these circuits. Instead of a resistor, we couple them to a transmission line. And what we make sure is that these detectors, so if the photons leak out of this system, that this is actually at 0 temperature. So we don't get photons back from the detectors, which of course one can argue whether this is correct or not in the experiment. But then the system itself, we model at final temperature T. So that's kind of the model which we put. So what is important for that our work actually works is, first we need good quality factors, which is actually realized in the experiment. So we want that, these are narrow line width, and in particular these two are not overlapping. So one is at low frequency, the other is a bit higher frequency, and the other is this condition, which is a bit strange at first. This just means it's a low impedance thing, but this doesn't mean that impedance on resonance is low with respect to quantum impedance. This just means that the impedance kind of away from the resonance is low. This is very important for us. So the impedance times the quality factor can become large. And then we kind of make the condition in such a way that we say the voltage is not necessarily exactly the sum of the two frequencies, as was done in the more simple theories before, but we allow for this detuning. And you will see later that we actually see interesting effects which come together, that the voltage is not perfectly aligned with the sum of the frequencies. So the parameters which you have in mind is the delta, tells you the detuning, and the epsilon, which is the strength of the driving, which corresponds to the Josephson coupling. So in the simplest setup, it's exactly the model as we had before, just in this case, non-degenerate. So we start increasing the driving strength, which means increasing the Josephson coupling. Classically, nothing happens here. And at some point, we hit the threshold, and then we see parametric oscillations. But the interesting stuff for quantum applications is this region below actually the threshold where you get classical oscillation. In this region, you get fluctuations, and the fluctuations feel already that the threshold is close by, and these are these quantum fluctuations which might produce entangled photons. So we are interested in this regime slightly below the threshold for our calculations. And so what we actually do, we actually say the fluctuations are small. That's why we expand in the fluctuations. So these are the phases of the Josephson, of the superconducting elements. So we expand in them. And so in some sense, our theory is only valid away from the threshold. And there's a small interval close to the threshold where the theory breaks down. But this interval is very small as long as these impedances are small, which we assume. So we're kind of close to the threshold, but not exactly at the threshold. And the method we use is called Keldysh path integral. I just want to point it out in a second what we do. So of course, it's an open system. So we have to kind of calculate the evolution of the density matrix. And the density matrix has two evolution operators because, because it's kind of on one side is the brown and the other side is the cat. And we call them forward and backward propagation because this looks like a forward propagation in time. It is like a backward propagation. And then kind of all the propagation is doubled, and that's conventionally drawn on this Keldysh contour, where on one side we put a plus, which corresponds to forward propagation, the other side we put a minus, which corresponds to the backward propagation. And then for each element which we have here, there's a certain action which we put in our path integral, and then we do this expansion, and then we evaluate the path integrals. If you're interested in this method, there's actually a book by Kamenev, and there's also a paper which explains it very nicely. So now to the results, which I think is the interesting stuff. Okay, so on one hand, we actually calculate the photon current, which is just how many photons leak out in cavity A or cavity B. And what we do actually this frequency resolve. So the question is at which frequency they leak out. Of course, typically they leak out at the frequency of the cavity, but then they might be slightly detuned from the cavity. So what we see is the following. And so here I will try to argue why it's interesting to look at from a theoretical point of view, to look at the detuning. And this is actually part which one can also then test experimentally, maybe in a future experiment. So we are interested in a situation where the voltage doesn't exactly fit the sum of the two natural frequencies of the resonator, but we have a little bit too much energy. And what we're asking is like, where does this energy go? Does it go, so which of the photons is actually emitted exactly at the resonance frequency, and which of the photons gets a detuning? That's a question. So first we look at it at the symmetric situation. So both of the resonators are not at the same frequency. This they cannot be because non-degenerate, but have the same line width. Yeah. So we analyze a situation where both of the resonators have the same line width. So let's say a resonator A is at lower frequency, resonator B is a slightly higher frequency, but both have the same line width. And we are close to the threshold. Then what we actually see is that they're kind of, nice to each other, and each of the resonator takes half of the detuning. Yeah, most of the time. We see the peak here is at half of the detuning. And one might say, yeah, this is all the time what happens, but this is not true. But if you, for example, drive only very weakly, you're kind of far away from the threshold, then what you see is that you get a double peak structure. And what that actually means is the following. So like half of the time, resonator A takes all the detuning, and resonator B is there without the detuning. Yeah. And the other half, it's the other way around. So you might even expect an entanglement. This is kind of a frequency entanglement between the photons, which then if you do measured photons which arrive at the same time, you actually figure out if this one is kind of at a higher frequency than this one is at a lower frequency, yeah? Or the other way around. And then what is also interesting to look at the asymmetric situation. What happens if one of the resonators is broader than the other? And I think maybe this you might have expected, but it's also nice to see it. So close to the threshold, then the resonator which is actually broader takes all the detuning. You see this line width become extremely narrow. So essentially all of the time this resonator takes the detuning, and the other one is left without detuning. And this even remains true at low driving. So in this case, they actually don't share the detuning among themselves. So, but now we want to analyze, is there anything quantum about this radiation which comes out? I mean, there's radiation coming out of these cavities. The question is there anything quantum about it? And when there is something quantum. So what kind of thing I have to do in the experiment that I see the quantum nature of the light. And the best way to actually do that is look at the correlation function. So it's not just the photon current, but you kind of correlate the photon current at one time with the photon current at some other time. You correlate that and you kind of normalize it such that it's naturally unitless, this quantity. So that's a conventional, what is called second order coherence. And for the second order coherence, what you can actually prove, if these photon currents are kind of classical random variables, so no quantum operators, no heads on top, then this Cauchy-Schwarz inequality holds. Yeah? Doesn't matter what kind of system you have. So if you violate this Cauchy-Schwarz inequality, that means this, this is the autocorrelation of the first resonator. This is the autocorrelation of the second resonator, and this is the cross correlation. So if the cross correlation starts becoming too large, then the system has to be quantum mechanical, because otherwise you cannot realize that. So in some sense, this is similar to a Bell inequality test. So once you violate this, you kind of are sure that there's some kind of entanglement going on in your system. So the question is kind of what is the autocorrelation? Of course, in an experiment you can measure it just directly, but theoretically the autocorrelation is 2. This is what you expect for chaotic light. So the light emission in one of the cavity is completely chaotic. The only correlated effect is the correlation between the two resonators. And so the N tells us how many photons we have. So this is kind of a measure of the temperature, like what's Bose-Einstein occupation of the different resonators. And what we actually want to have a cross correlation which exceeds 2. By that we show that the system is quantum mechanical. So what our results show is that at the threshold it's not good to measure the quantum nature of the light. Way below the threshold is also not good, so it should be kind of in the middle, yeah, which makes a lot of sense. And I think low temperature is better than higher temperatures makes also a lot of sense. So you have to be at low temperature, but in particular, there's one temperature, and sadly it starts already quite early. So at half photon occupation, there's actually no way that you ever violate this Cauchy-Schwarz inequality. But then, having this flexibility that we actually allowed for different bandwidth of the two different resonators, and we allowed for detuning and stuff, we actually realized that this condition where you cannot violate the Cauchy-Schwarz inequality depends kind of on the asymmetry. So now you might go there and try to understand, maybe asymmetry helps you to relieve these restrictions. And what turns out is the following. So now we have a parameter gamma, which tells us like how asymmetric the two resonators are. So you compare one of the resonators to the other resonator, and if gamma is 0, then they're completely symmetric, as we've seen before. And then on the one side or the other side, one of the resonators is more has a bigger line width than the other. So in the situation where actually the occupation of the two resonators is the same, the best what you can do is having both the same line width. Yeah? But this is never the case, because as you remember, the non-degenerate amplifier is in such a way that you have actually two resonant frequencies, and they are not, one is lower and the other is higher. So in the end, what you have experimentally is one has, so the lower in frequency one has a higher occupation than the other one. And so in that case, what you can actually do, you can actually you can afford a higher value of temperature by allowing for detuning. So if you optimize your experimental setup, it's actually useful to use the asymmetry. And the way you have to do it is the following. So you have the frequency, the resonator at the lower frequency should be the more narrow one, and the resonator at higher frequency is the more broad one, such that together you actually optimize the situation that you can violate this Cauchy-Schwarz inequality. Another thing which is quite interesting, and we actually written a paper about that. So if you're interested about this, then please take a look at that. Is that actually, if you approach a threshold, there's this divergent timescale, yeah? And this is quite well known. So if you look at the cross correlation function between the A and the B oscillator, then typically it starts out somewhere around 2, and then it decays. And there's one time scale associated to that, which is at which time it decays towards 1, which it does at 1 time. And if you do the calculation, you see that typically it's very close to exponential, the decay. And then this time scales is actually diverging once you reach the threshold. So this is actually very similar to a phase transition. Yeah? So in phase transitions, it's actually length scale which diverge. This is a non-equilibrium system, and in non-equilibrium system, the time plays the role of the position. So what you actually have is that the time scale is diverging once you approach the threshold. And what you can actually show is that there's universality appearing close to the threshold due to this diverging time scale, the same way as universality is appearing in static statistical mechanical system, where everything just in the end depends on this time scale and on some symmetries, but not on the specific situation of the experiment under hand. So more information you actually find here. So with that, actually, I want to conclude. I want to kind of highlight our main results again. One is we actually use this Keldysh path integral formalism, and if your theory is maybe you want to take a look at it, it's actually, you know, what we do the expansion is in a parameter, it's kind of well controlled for low impedance systems. And that's kind of the only thing which we have to do. And experiments are very often in this low impedance setting. And we've seen like 2 talks before, it's kind of hard to go in a high impedance setting where you have to make thin films and kind of put inductances everywhere. But typically you're in a low impedance setting, and then this formalism is very naturally suited to calculate essentially everything which you want to, which you can observe in the experiment. Another thing is that this detuning is quite interesting. And in particular, I like the situation, which is the black one, where we kind of have 2 resonators, which are having both the same line width. And then if you drive them, then there are 2 situations. The 2 things happen at each 50% of the time, where they kind of cannot decide who takes the asymmetry. And then you can look at actually entanglement if you kind of do frequencies selection. And the other thing I showed you, like even without this frequency selection, you see violations of Cauchy-Schwarz inequalities, but you have to go at low temperature for that. In particular, we've seen that the blue line was at half of occupation of half of a photon, so you have to go lower than that in order to see this violation of the Cauchy-Schwarz inequalities. Okay, I think with that, I want to end. And I want to thank you for your attention.
Yeah, thank you very much, the speaker, for a great talk.
Thank you very much. Yeah, sorry again, problem with connection. Let's thank the speaker for a very interesting talk. Questions, please. Well, as I understand, one of the key results is the ability to distinguish between classical and specifically quantum correlations between emitted photons. Am I right?
Yeah.
Yeah, great. So this is indeed important. Any more questions, please? Then let's thank the speaker.
Yeah, I can ask one question.
Yes,
thanks, Fabian, for the talk. This is interesting for many reasons. For the axions, do you think, this kind of 2-cavity approach might be used to detect the very weak signals? Like, I'm thinking that if one of these resonators would be the axion cavity, and the other one would be maybe just a superconducting resonator outside. And would there be some way that if in the axion cavity you get very weak signal, then you start to shoot photons out from the other resonator, for example, or just a crazy idea?
No, I like crazy ideas, and I have to say I didn't think too hard about this. But I mean, all what we know, I think my answer goes back to the usual theory of amplifiers, no? And we know that degenerate amplifiers have some advantages, and kind of non-degenerate amplifiers also have some advantages. Yeah? So this 2-cavity setup is non-degenerate amplifier, and it has the big advantage that you actually amplify all the signals. Yeah? So you don't have to be phase matched. So in cavity A, you don't have to be phase matched in order to amplify. No? And so if you kind of detecting a signal which you don't know what the signal exactly does, maybe that's a good way to go ahead. No, of course the degenerate one is kind of a better amplifier by I think a factor of 2 or so, but but this has a big advantage that it amplifies all signals in with all phases. Yeah. But that's all what I can say to that. Yeah.
Okay. Thank you very much. More questions? Okay, then let's thank the speaker for very interesting talk, and understand the coordinators of the project would want to say a few words. So thank you, and I am removing myself from my chairman position.